Hello and welcome back to Josh Does Math. Today we got a problem involving the differentiability of a function. So consider the function f of x defined by, and here you can see it's a piecewise function. It's going to be x squared if x is greater than, or if x is less than or equal to a. And it's going to be mx plus b, so some linear function, if x is greater than a. So right now, before we keep going, I'm just going to try to get an idea of what's going on. So if x is less than or equal to a, we'll just say that a is over here. So that's a. If x is less than or equal to a, it's going to be a parabola. So I'll just draw a parabola and it gets cut off right here. And that point is included. Okay, and if we're greater than a, it's going to be some linear function. And I'm going to draw the linear function just down here. So it's not included right there. And there's our linear function. So this is kind of what this graph is going to look like. They say where a, b, and m are constants, okay? Find what values m and b must have in terms of a in order for this function to be differentiable at all points. So for the function to be differentiable at all points, a couple of things need to happen. It needs to be continuous. Continuous for all values of x. And what else needs to be true? Well, we need to have no sharp points. In other words, the left-hand limit of the derivative and the right-hand limit of the derivative need to be equal. So I'll say right-hand limit of derivative needs to equal left-hand limit of derivative. Just some abbreviations there. But, I mean, that makes sense. You need to have the same limit coming from the left side and the right side of the derivative. And if you do, that means that the rate of change coming from the left to right is equal. So it's a smooth point. If not, it's going to be a sharp point, and you can't take the derivative at a sharp point. So these are the conditions for this function to be differentiable. And we want the function to be differentiable at all points, so we need to make both of these true. Well, how about we start with trying to make it continuous? Where is this function not continuous? Well, you can see the only point where it may not be continuous is this right here. That's going to be a jump discontinuity if we let it do this and go up and then move down and resume the function right there. So we want this to match up. In other words, we want to shift right here. We want to shift this linear function up to there. And in order to do that, we're going to have to mess with these constants that they give us. So at x equals a, we want x squared, the left side, to equal the right side, mx plus b. This is what we want to be true at x equals a. Okay, so for x, we can just plug in a. A squared is equal to ma plus b. So that's one equation right here, and we're solving for a. So we're solving in terms of a. So a doesn't need to get canceled out or anything. But as you can see, we have two other variables here, so we're going to need some other equation besides this. Right-hand limit of d needs to equal the left-hand limit of the derivative. So first of all, what is the derivative coming from the left side? Well, it's going to be the derivative of x squared. And we know that that is 2x. So coming from the left side here, we know that I'll say df dx is equal to 2x. So that's coming from the left side. I'll just break it up like this. Okay, what about coming from the right side? What's the derivative? df dx is equal to, it's just going to be m. We're taking the derivative of mx plus b. That's just m. So these are the derivatives from the left and right side. So now we're saying that the limit as x approaches a from the left has to be equal to the limit as x approaches a from the right for the derivative, and that's the derivative from the left and the right. So the derivative itself is a piecewise function. And just like how we said that the point on the left side has to be equal to the point on the right side right here, the same is true of the derivative. They need to be equal coming from either side, the limit, as they approach that value of a from either side. And as they get closer and closer, they need to be equal to each other. So we can say that 2x is equal to m. We're setting the derivative from the left side equal to the derivative of the right side at x equals a. So just plug in a to this equation. So 2a needs to equal m. Here's our two equations. We can now solve for m and b in terms of a. So I'll solve for b first. So I'm going to plug in 2a for m to this first equation. So a squared is equal to 2a squared plus b. Subtract 2a squared from each side, and I end up getting b is equal to, it's going to be negative a squared. So that's the value for b. So now, what about the value for m in terms of a? Well, that's even easier. We were given that one. So m is equal to 2a. So that's the value for m and b that will make these equations differentiable at some general x is equal to a. In other words, you give me our a value, I can tell you what m and b are supposed to be in this linear equation right here, such that the function is differentiable at all points, including x equals a. Thanks for watching.